Awesome. There we go. All right. Thanks for joining us this morning. We've got a really good webinar coming up with a really good presenter. I was lucky enough to run into Alex Meaney at the ACA conference in San Antonio a few months ago. And then about 15 minutes of speaking with him, I knew I had to get him for some webinars because really knows the background and the science of it. And then he can, what I like about him, no nonsense, and he dispels some common myths in the industry. Today, one of those myths we'll be talking about is the ton, and there's no such thing as a ton. Some kind of housekeeping. There's a little hand icon or a Q&A icon. We'll hold all questions for the end. We should have time for questions at the end, and we'll do those. And then just some for ICC CEUs, Mariel will send out a course evaluation. If you fill out the course evaluation, then you can get ICC CEUs for today's webinar. Non-HVAC related, but on Wednesday, back to our normal Speakers Bureau series, we have a continuous insulation for code compliant high performance walls in type 1 through 4 construction coming up. One of the PIMA presenters will be doing that for us. And then I will be in San Antonio on May 16th, Lubbock on June 4th, and El Paso on June 11th for a 2-hour in-person JSD, flex duct, best practices, installation guidelines, manufacturer's installation instructions, just kind of a residential HVAC 101 training on those dates. Thank you for the State Energy Conservation Office and TACA for helping with today's webinar. Most of you know who SPEAR is. If not, we cover Texas and Oklahoma. We're a regional energy efficiency organization. Anything energy code related, don't hesitate to ask. The price is always right. Any way I can help y'all out whatsoever is free. So happy to do it. And then we have another webinar coming up, business case for street lighting retrofits. You can contact Cassidy Ellis. You see her email down there, or just send a note with the course evaluation. So with that, I'd like to turn it over to Alex. Let me get him unmuted. And Alex, you want to go ahead and share your screen? I'll unmute you now. You are unmuted. Just share your screen and you are good to go.
Okay. So I'm going to stop sharing yours and start sharing mine. Let's see.
Looks good.
Looks good? Beautiful.
Yes,
all right. First of all, I'd like to apologize for the clearing my throat and occasional cough. It is allergy season, and they recently released the rankings of the worst places to be for allergy season, and my area made number 6 on the list, so good for me. I didn't have allergies till I moved here. Yeah, my name is Alex Meaney. I'm currently the head trainer for MyTech Wrightsoft. You probably have heard of us. We're kind of the load calculation people. Of course, as most companies will tell you, we're a lot more, but that's where we're famous. But we're also the, so that's Manual J. We're also the Manual D people, and hey, we're also the Manual S people, which is kind of what we're here to talk about, right? I picked the title for this presentation. There's no such thing as a ton, because frankly, I like breaking people's brains a little bit. There are a lot of things that we know about the HVAC industry that turns out aren't true at all. And when something that you know is untrue, that can cause a lot of problems because you build more and more knowledge on that as you go. And that's what can lead to a lot of sort of mistakes. And it also is what leads to sort of people rejecting ideas and things that work because it competes with or runs contrary to these things that you quote unquote know that turn out not to be true themselves. And that's where the sort of friction kind of comes in. So I'm going to get this contact information off of here. We will bring that back up at the end. If anybody was in the middle of writing that down, I apologize, but I believe they're recording this anyway, and it shouldn't be too hard to get a hold of us through Jason or any other means. So, oops, I shouldn't have left that on. Oh well. So some of you, if you were reading that, you get the answer to our trick question here. So like I said, I do like to start, or I do like to sort of break people's brains a little bit. So I like to start off with sort of a weird brain teaser. When I teach my classes, I call this a pop quiz. It's not really a pop quiz. I don't ever make anybody write down the answer, but I would like to go through this exercise. We're going to give you guys a little pop quiz. You don't have to answer. Don't put it in the chat. I just want you in your head to try to answer the question I'm going to ask you here in a bit. First, let me tell you about these two houses. Okay? They are neighbors. Now, these neighbors, they live in a part of Texas where basements are a thing, which I realize is a very small corner of Texas, and even there, not very popular. But you know what? Humor me. We're going to have a basement in this example. If you like, you could make it a first floor, second floor, two-story home with ductwork in between the floors in like a web truss or something. But regardless, I have two houses. The house on the left has 2 stories, and the ductwork is inside the conditioned space. This homeowner has a smaller footprint house, but technically a larger floor area. But because the first floor of this building is actually below grade, there's not a lot of cooling load here. And so despite having more total area and technically a larger house, this homeowner has the same load as the home next door. Now this homeowner here, with their duct system inside the conditioned envelope, had a request for us in that they wanted to maintain 72 degrees inside the house. And according to Manual J, by the way, that's legal. You're allowed to do that. So we did. The only thing that will come into conflict with that is local codes and sometimes some power company restrictions for rebate programs and that kind of thing. So we designed them a system for 72 degrees, came up with a load, and weirdly, and we're going to pretend it's weirdly, it was actually just a lot of work on my part, their neighbor with a completely different house ended up with the same load. Now this guy over here is just a 1-story house on a slab, right? So his ductwork is up in the attic, and his ductwork is not of the best quality. It's a flex spider system that's held together with essentially zip ties. There doesn't seem to be any tape or mastic going on here. It's pretty darn leaky. The return run is kind of long. It's got a unit on one side of the house, and the return is kind of on the opposite side. So we're not really happy with his duct system here. We recommend to the homeowner that they replace this duct system. And of course, in the homeowner's infinite wisdom, that's just another way for us to make money off of them. They just want me to replace the system without touching the ductwork. They just want, new boxes. And like dummies, we agreed. And so we've decided to take on the role of replacing this new system, or replacing this this old system with a new system without touching the crappy ductwork that's up in the attic here. So I've said a couple of times that these two houses have the exact same, and I mean exact same, down to the BTU, the exact same load, right? So we did the load calculation. We did it, let's assume we did it perfectly. I'm the Wrightsoft guy, so I would hope I did it perfectly. Also, these are made-up houses, so we can say we did it perfectly. And the funny thing is, these two neighbors have exactly the same load. Same sensible, same latent, same total. Everything about the loads here is the same. Now, the pop quiz, the trick question is, I want you to guess which of these houses needs a larger system. Okay? One of these houses needs a larger system. Which one is it? Right? Is it the one on the left with the ductwork in the conditioned space? Is it one on the right with the ductwork up in the attic? Which one needs the larger system? All right, we think we got it. So it turns out the one on the left needs to be a larger HVAC system, a larger air conditioner. Okay. If I take a look at the numbers In this home, the 4-ton condenser with the 4-ton coil and 1400 CFM gives us a capacity in this house of of exactly 37,789 BTUs, right? So about 37,800, right? In this house, a 3.5-ton condenser with the same 4-ton coil and the same airflow, same 1400 CFM, is going to give me 38,400 BTUs. I needed the 3.5 in this house. I needed a 4 in this house. So first of all, they have the exact same load. Why do they need different air conditioners? Second of all, what the heck? Why does a house with a duct system in the conditioned space need the bigger system? Wouldn't the system with the bad ductwork be the one that needed to be bigger? So a couple of things that are happening here. It was a trick question. Warned you that was the case, right? I had to be a little sneaky on you. There was a clue. If you were paying real close attention, there was a little clue as to why this is happening. I tried and tried and tried to get this example to work with a full half-ton of difference in the end capacity, while leaving the conditions between these two houses as similar as possible. What I tried to do is just change the duct location and see if I could get it done with that, and I couldn't. So what I had to do to make this a half-ton difference between these two and get the big shocking results at the end, I had to cheat. I didn't cheat, I told you guys, but I had to cheat. I had to make this house 72 degrees. And by making this house 72 degrees and by having a crappy, specifically return in this house, I was able to create enough difference in the return air conditions that the capacity of the system would change enough that we'd be looking at 2 different size units with exactly the same load. So before your brain just absolutely says, that's it, I'm out of here, we're not listening anymore, this guy's obviously off his rocker, I want to say, if we had gotten our way, and if we just went to this house and replaced that duct system with a better duct system, tore out all that flex and put in a better duct system, an insulated, a sealed duct system, the load on this house would no longer be the same as the load on this house. The load on this house would be significantly lower, and we'd be looking at putting in a smaller system, okay? So we didn't compare this house to that same house with a better duct system. We compared this house to a different house with a better duct system and a cooler return air, and that's what changed what the needs of the system were. But it turns out there is no such thing as a 3-ton load. The load doesn't tell you what size equipment you need. And I know that's, what the heck does it do? Well, it tells you how much heat the building gains, how much moisture the building gains. And in Texas, this is less of a worry, but if you go into North Texas and Oklahoma, it's kind of a big deal, how much heat the building loses as well. That's what a load tells you. A load is about the building, not about the equipment. The equipment itself will tell you about the equipment, right? The equipment manufacturers will tell you about their equipment. And your job as an HVAC contractor when designing a system is matching those 2 pieces of information up accurately. And if you want to do it accurately, let's start talking about, so what this is, the procedure I use to get to this conclusion, which is, by the way, 100% correct. This is, don't go looking for any weird angles on why this might be wrong. This is right. I mean, do what you want to do. You want to find a weird angle and throw it at me. We can have that discussion when the rest of this is over. But it's not going to be. You're probably going to be disappointed. If we look at the Manual S and we look at what the procedures are, there is sort of a set of rules in the Manual S that you know, as these things work, as codes work, they don't sort of prioritize rules. It's either a rule or it isn't a rule. And so I might talk about sort of the first rule and the second rule and the third rule. That's all me making that up, right? That's all just me assigning that. Although I will say that this first rule of the Manual S It is the first thing the book says. Literal first thing the book says. And this always bums out inspectors, and I know that that's a lot of you guys. But the first thing the manual S says about equipment selection, about choosing your equipment, do not use AHRI capabilities. Do not use AHRI data when selecting a piece of equipment. It is not up to the task. So, so let's talk about why. Okay, so here is my terrible sketch of a house. Right, I'm aware it's terrible. It is functional for the purposes of our conversation. And so you guys should probably know, I probably should have led with this, but I know we are never at capacity when we start. So I'm a, excuse me, an EPIC certified instructor. So I'm certified by the ACCA to teach the Manual J and the Manual D and the Manual S and Manual T and ZR and a few other books. And so this isn't just, you know, the dude who works for the software company. I teach residential design just about every day. That having been said, I'm not a former contractor or engineer. And we will get to a point, especially when we start talking about refrigeration, superheat, subcool, the difference between R22 and 410A. I've got a good 10,000 foot view handle on the situation and can explain how this works. 10,000 foot probably being a little ungenerous with myself by saying that. But we will get to a point if we start talking about refrigerant flow and how it works, where my knowledge hits a wall. And I've always felt as an instructor that it's my job to A, warn you that that point exists, and B, tell you when we do. So if the questions do start to veer toward that, if you want me to explain why, you know, refrigerant works the way it does, I'm definitely not going to be able to answer that. But you know, that's for me to figure out. You can ask me whatever you want when we get to that part. So this is my you know, very basic sketch of how a system, you know, works within a house. And we're going to keep things really simple here, right? So if you're kind of like me and have a tenuous relationship with, at best, at understanding of superheat and subcool, we're going to say things like, this is the cold part and this is the hot part, okay? We're going to keep it at basically that level. I think we can all handle that, all right? So, and I don't care if you think that it's expansion and compression that causes the temperature to change, or magic. It doesn't matter for the purposes of this conversation, actually. So, so you can relax if you're a little weak on the whole how refrigerant cycle works thing, right? What we need to know is that out here, refrigerant gets hot without adding energy, and in here, refrigerant is cold without adding energy, and it's thanks to the miracle of compression and expansion. Now, when AHRI tests a unit, right, and they see how that unit works, their test conditions are that the outdoor unit will be sitting in 95-degree air, which in parts of South Texas, that's a little shy of what you would want it to be, right? Like, hey, we're going to be hotter than that. But for a large part of the United States, 95 degrees is a typical hot day. And so it makes sense for about that temperature to be the rating point. And there are parts of Texas where that's about right. And there are parts of Texas where that's a little high, and even some northern parts where it's a little low, although not very. So that's not the crazy part. The crazy part is here. So when they're running this unit, right, and they're blowing air across this cold part, across the coil, and first of all, the amount of air that they're blowing across that coil, it's whatever the manufacturer specifies, right? So typically it's between 350 and 400 CFM per ton, but it is up to the manufacturer to specify what that airflow is, right? It used to be there was 400 CFM per ton, and now it's however many, you know, CFM the manufacturer says is per ton. So that's sort of up in the air. It always was kind of up in the air, actually. It's just most manufacturers stuck to 400 per ton. That's not actually a rule. That's not actually a thing. It's not a thing in physics. It is up to the manufacturer to decide how much airflow they're going to design the system for, and always has been. And so when we're told that it's 12,000 BTUs per ton, we're going to get to that one later. That's a fun one, which we know is not true. Even if you look at AHRI conditions, you know, a typical 3-ton unit isn't 36,000 BTUs, and it hasn't been for a long time. So this nominal capacity idea is already sort of like, if I told you there's no such thing as a ton, you might think that what I mean is the manufacturers aren't able to get a full ton out of what they call 3. That's nope, still not really the case, but it sort of introduces the idea anyway. So I'm hitting all the normal stuff. Here's the crazy thing. You probably spotted it already. The return air conditions. When AHRI rates a unit, it's running this system with a return air temperature of 80 freaking degrees. That's not a typo. That is, it's common knowledge. It's not common knowledge. It should be common knowledge. But they're not hiding it from anybody. This is the temperature with, by the way, a 67-degree wet bulb. So if you're not familiar with the term wet bulb is a measurement of humidity, right? There's actually a thing, pardon my sort of physics lesson here, but there's actually a thing called a sling psychrometer. They don't use these things anymore, but this is how they came up with the term wet bulb. If you wanted to measure humidity, you would take a thermometer and you'd measure the temperature of the air, right? Just a regular thermometer, in the shade outside, right? And it would say, the temperature is whatever, 95 degrees. And then you would take this thing called a sling psychrometer, which was a thermometer that had some cotton wadding around the bulb at the base. And it was literally on this sling. And so you would take the cotton wadding and you would wet the bulb on the bottom. And then you would literally swing the thermometer around in the air, right? And as you swung the thermometer around in the air, that water would evaporate. And as we know, evaporation causes cooling, right? That's why we sweat, right? Evaporative cooling. And so what would happen is that water evaporated, the temperature would drop. The less humid the air was, the more dry the air was, is a better way to say that. The more dry the air was, the more evaporation would happen. And so the more that temperature would drop. The less evaporation happened, the less that temperature dropped, the more humidity must have already been in the air, right? And so the closer together these two numbers are, the more humidity there is. The further apart they are, the less humid the air is. And there are some things that you can know just from a wet bulb number, to be honest. But what this is this is 50% relative humidity, roughly, at 80 degrees, right? So not only is this air very hot, it's also very humid, right? If you wanted it 75 degrees in your house and you wanted a 50% relative humidity, you'd be looking at about a 63-degree wet bulb. This one's 67. So a much higher humidity content and a much higher temperature, right? This is a giant outside air duct dumped into the return. This is a giant amount of return air leakage, which used to be a thing, by the way. And go back long enough in AHRI's history, you could definitely make the argument that these were appropriate numbers for a return air. But these days, if you were an HVAC contractor out on a call where there was no cooling, and you took a reading right here at the return and saw the temperature of the air was 80 degrees with a 67-degree wet bulb, there isn't a technician on earth who would say, well, I guess there's no problem here. I wonder where this problem is, right? If they saw those readings right here at the return, they would have identified the issue with the comfort in the home, and that is that the return air was extremely hot and extremely humid, and there's a giant leak somewhere that they should fix. And this is how AHRI tests their systems, right? So this is what happens when things get hot. Now, I teach all around the country. And when I teach all around the country and I start talking to contractors about, the kind of pain in the butt it is to do this right and why you should do it right and why it's so important, I will sometimes single out certain areas as being, just be thankful you don't live here. It could be a lot harder. And I'm sorry to say that in a lot of the areas I go to, I say, well, be thankful you don't live in South Texas near the Gulf, because that particular region, you have a very tough job if that's where you're at. I'm not saying you shouldn't live there. It's very nice down there. I go down there all the time, right? Who doesn't love, the island and Corpus and whatever. But as far as an HVAC contract is concerned, your job is harder than just about anybody else's in the country. And I'm not kidding about that, right? Because it's hot outside. And so what does that do? Well, that reduces my ability to reject heat, right? So as this cycle runs, right? And that cycle is, I'm absorbing heat here at the same rate, but I'm not rejecting it as fast, right? And one of the hardest things to take into account about system design in general and about how an HVAC system runs is the time effect, right? These are dynamic systems, right? This thing runs over the course of an hour or several hours, right? So what happens to this return air temperature as you run the machine? Oh, it's going to get cooler. It's going to get drier, right? What happens? So what happens to the temperature of this coil if I'm not getting rid of the heat as quickly, right? So some people say that this will be warmer, right? And other people say, well, no, that's not how refrigerant works. And, you know, all right, so you both have a point there. But if you say over time, the average temperature of the coil, if you phrase it that way, that's when you get to say, well, this coil would be warmer because you're just not getting rid of the heat as fast. And so two things are going to happen when it gets outside, hot outside. You're going to lose capacity because you're just not getting rid of heat as quickly. That's just going to happen. So a system is going to have less capacity when the temperature goes over 95 degrees than what AHRI rated it at. And it's going to have less moisture removal capability, all things being equal, right? Your percentage of moisture removal is going to drop because the average temperature of this coil here is going to get warmer, and it's not going to cause as much condensation. And so South Texas near the Gulf, we have very hot outdoor temperatures, maybe not 105, but we're over 95, right? 98, 99 are normal design conditions for there. And you have some of the highest moisture removal needs in the country. You have to be very careful how you match the system up to be able to do both of the jobs you need to do in a home like that, right? So this is the one that caused our example to need a half-ton difference. If you reduce, and it's the one that's the hardest to wrap your brain around. If you reduce the temperature in the return air, and when you reduce that temperature, you leave the relative humidity the same, okay? So remember I said that a 67-degree wet bulb would be a 50% relative humidity. So about 50% relative humidity. I think it's 62.5 actually, but who cares, right? 75-63 is generally considered the sort of comfort, standard for a 75-degree temperature. This is about a 50% relative humidity here as well. And the reason I add that caveat is because dropping this temperature without dropping this one, right, and just letting the humidity, the relative humidity go way up, you're not going to see as big a difference in the actual capacity. But when you drop the return air temperature and leave the relative humidity the same, relative humidity, not wet bulb, you get a significant decrease in the capacity of the system. Because, and now, so this is where I lose people, so think about this, guys. This is the cold part. Its job is to absorb heat. When you think about it, its job is to warm up, send that energy outside so we can reject it, right? And so if your job is to collect heat, warm up, is it going to be easier or harder to absorb heat from cooler, drier air? Well, it's going to be harder, right? You want to warm up faster? Go someplace warmer. And so when you drop this temperature, the capacity of the system drops. Now, what it does to moisture removal capabilities is a little bit of a complicated question because we are changing the conditions of the moisture removal needs of the envelope, right? We're assuming that this is already fairly dry air in order to create this example. So technically you do lose latent capacity, but you're only losing latent capacity because you're losing latent load. It's kind of a push, okay? So if it's just drier though, right? Even if you didn't make it colder, if you just made it drier, because condensation is about twice as energetic as conduction is, right? When we look at the performance of the different kinds of heat transfer at the coil, when we reduce the moisture in the air, we significantly reduce the capacity of the system. So another area that gets name checked in my classes will be Arizona. So some parts of Northwest Texas could somewhat compete here. In Arizona, you go to Phoenix, it's gonna be like 115 degrees in the shade. That really hurts the capacity of the system. And then you get the second hit of this reduced return air wet bulb, and that also reduces the capacity of the system. You know what the average capacity is, roughly speaking, back of the envelope math, for like a 3-ton system in Phoenix? It's about 28,000 BTUs, right? No joke, right? 27, 28, maybe pushing 29, but that's a maybe. That's if you're in one of the areas that's a little maybe higher altitude, a little cooler outside. Because the hotter outdoor temperature is driving the capacity way down, and so is the drier air. Okay, because theirs is like 59 on that wet bulb, by the way. So most HVAC professionals know what happens when you start tinkering with airflow, right? Because and that makes sense, right? Because the HVAC professional is kind of in charge of that. They're kind of responsible for that, especially with new systems, right? 350 CFM per ton. If you're originally rated at 400, that's going to put less air across this coil. So that's going to reduce the capacity, and it is going to increase the proportion of moisture removal, right? So whether it actually increases the total BTUs of moisture removal or just the proportion of moisture removal is a conversation I don't want to bother having. It gets kind of technical and it misses the point, right? The proportion of moisture removal that the system does goes up when you reduce airflow, right? So whether or not it's quote unquote better at removing moisture is not that conversation I want to have. But if you have something that's short cycling and you're having moisture problems in the air, reducing airflow tends to alleviate that issue. And if you think about it, it sort of, by pouring less heat into this, right, because this is the rate of flow across the coil, when there's less air going across it, there's less heat entering this part of the system. You get less heat going in, you get heat going out at the same rate, the coil is going to get colder faster, right? So that time effect comes into play again, right? And so you do slightly better moisture removal as a proportion of total capacity, and you reduce the overall capacity of the system, which, again, you can see how that would solve a short cycling system that's not doing enough moisture removal. So the flip of all these things is true. If it's cooler outside, not a huge problem in Texas, but you go in some of the high altitude areas, maybe a little bit, and you get less capacity. If you increase the outdoor temperature, or the indoor return temperature, you can actually increase the capacity of the system, but it's going to start to blow warm air out the other side, okay? The ratings of how much capacity the system has is just a rating of how much heat it moves, not how comfortable it is in the house. Right? This is not a good thing. I don't want to see this. Okay. You would, and by the way, for a couple of these, this one included, this increases capacity up until the point you saturated the refrigerant and it can't hold any more heat. Right. So there does come a point where there's no return on, no improvement on doing this. So this is not a good thing. This is not you don't fix any problems doing this, because increasing this, remember the example from the very beginning, increasing this increases the load on the system too, right? So you're always going to need a bigger system when you start pushing this thing up, right? Relatively speaking, whether or not it's a full half ton bigger, who knows, right? So increased wet bulb does the same thing. It increases capacity and increased airflow up until the point where you're saturating the refrigerant. It increases capacity. But because you're pouring heat in so much faster now, this coil is going to take longer to get cold, right? And so that average temperature of that coil is going to increase, and it's not going to do as much moisture removal. And so when you increase the capacity in this way, you decrease its proportion of latent BTUs and its proportion of moisture removal, right? And the reason all this is important, guys, is this is often what you're doing. So this isn't what you're dealing with in Texas. I probably should have changed that. But man, this stuff is all over the map, right? What's the outdoor temperature? What's the indoor temperature? What's the indoor humidity? This is the big question, right? And so what we need to answer this question is we need some help from the manufacturers. Various manufacturers have various tools for doing this, and I've got some really cool, good news for the end of this session. And it does involve making Wrightsoft look good. All right, sorry, but they signed my paycheck, and also we're really good at this. So yeah, hey, great. Oh, I forgot about this. A guy somewhere in Texas, for all I know, maybe he's on this call. It'd be great. Who's going around telling everybody how our system oversizes things and how their tool is the one that doesn't. And boy, do I have a bone to pick with that guy. Because he's messing that up really, really badly. His example is really, really wrong, and he's like dead incorrect, and it's driving me a little nutty because I keep getting emails about this guy. But I'm not going to take it further than that. I'm not going to name check her and pick a fight here over somebody I'm doing a favor for somebody doing a webinar. But anybody who tells you that a load is a this many ton load, they're wrong. They don't know what they're talking about. Stop listening and move on. Okay, that is how that works. Okay, because this is the capacity of a system. This whole stupid chart, which doesn't even fit on the darn page. This is the capacity of a system. Okay, and this little yellow square here in this giant sea of numbers, I don't care if you can read that or not from where you're sitting. I just want you to look at the big picture. Look at all the numbers and look at this thing. That is what AHRI tells me about this piece of equipment. This is reality. This is AHRI. And by the way, I'm not highlighting both of these yellow numbers in yellow. I'm just highlighting this one. Okay. The first reason you should know that AHRI was never meant to be a tool for designers who would design a system and choose the right air conditioner for the job is it only ever gave you one number, a total capacity, right? I am not throwing shade at AHRI. If we had a representative of AHRI here, they would tell you, yeah, our tool is not meant for that. Our tool is for power companies and homeowners to be able to compare efficiencies and compare apples to apples what the capacity of a system would be, right? Because a lot of manufacturers have different charts, right? They use different design set points. They use different criteria. And so it's very difficult to say, is this system better than the next guy's when the two guys aren't publishing data the same way. It's very difficult to do those apples to apples comparisons. And that's why we have AHRI. And they're very good at doing that, right? So, you know, don't walk away from this being, boy, that Wrightsoft guy hates AHRI. No, I hate it when they misuse AHRI, right? Like I said, if Warren Lumpson were here, he would say, yeah, our tool isn't for this, right? Of course, we only give you one number, right? We're doing apples to apples comparisons. That's all we're trying to do, right? We're just trying to rate how efficient it is at giving you BTUs. You want to know how good it is in the house? Look this up. They would agree. That's why the manufacturers still publish this data, by the way. There's some good news here, too. Let me give you a little sneak peek at the end. You don't have to use the big charts. I use the charts to demonstrate what happens here and to show you the real numbers because this is a real piece of equipment. And so this real piece of equipment here, I'm not telling you who makes it. It's a 3-ton unit that AHRI tells me is 33,600 BTUs, okay? The thing is it's not 33,600 BTUs, and we've sort of learned that, right? We've established that a couple of times here, but let's look it up under real world conditions. Let's say it's 105 degrees outside, which I'll admit is not exactly the design temperature you're looking at in most areas in Texas, but we're going to use it anyway, okay? Because I don't want to use 95. It's just a little too easy, right? So when you're in between these numbers, you can do a thing called interpolation, which gets really math heavy, and I don't want to, this is conceptual, I don't want to lose people, I don't want to, but you could take a weighted average between these 2 points, which if it was just 2 points, it wouldn't be that hard. The problem is there's a lot of different points that you can quote unquote interpolate, and that's what they have spreadsheets for, and that's what they have, well, that's what they have software for. It's why they have Wrightsoft. So it's 105 degrees outside. My homeowner wants it 75 degrees in the house. That means if 50% relative humidity is what I'm looking for, and I have a very well-sealed return and no major outside air dump into it, which depending on the situation may not be true, right? But let's say it is. The capacity of this 3-ton system is 29,600 BTUs. Now, when I was taught how to do this, that's a 2.5 ton, right? That's 30,000, less than 30,000 BTUs. What do you mean this is a 3-ton system? Yeah, this is a 3-ton system, guys. It's got 36s in the model numbers. I'm not going to show you the actual model numbers because I'm going to tell you something about this system. It ain't great. I picked this system for a reason. It's got a flaw. It's not a bad system. It's not an evil system. It's a system I would put in somebody's house. But this system is not particularly good at removing moisture. In this particular combination of sequence of events here, only 11% of its energy is being spent on latent capacity. All of the rest of it is sensible, right? So if we look at, for those people who didn't like the 105 degree thing, if we look at the 95 degree thing, and we look at the 75 degree, and we look at the 63 degree. This is, a lot of power companies consider this like, the Tennessee Valley Authority considers this to be the gospel right here. These are the magic numbers. But if you're hotter than this, it's going to be worse. You could be looking at less than 30,000 BTUs. But even under what most people would consider normal conditions, this system only has 31,000 BTUs. And 86% of it is sensible. And so if you do the math, because that's what that is, that's a percentage of the total capacity that's sensible. When you do the math, if it's 31,160 BTUs, it's 26,800 sensible BTUs and only 4,300 latent. Now, in the new construction market, which, by the way, this is the engineers who make this equipment, this is what they'll tell you. Like, well, of course it doesn't. It's made for the new construction market. You don't have to do all that moisture removal in new construction. Do you? Maybe, right? What if you've got a giant house that has 3 systems in it, and you do one return air duct for the whole, or one outside air duct for the whole darn thing, and all of that outside air gets dumped onto one poor little system? Now you're going to have a lot of moisture removal for that one system, and this particular system is really bad at it, right? This is 4,300 BTUs of latent capacity, okay? Out of all the BTUs now, so why is that bad? What's bad? What's good? All right, so it's kind of a tough question to answer. What's bad? What's good? The old standard used to be assume that a typical average system in the United States was 70% sensible and 30% latent under these conditions down here, right? Which would probably be about 70, between 73 and 75% in this range here, okay? So 80% would be, kind of below average, and 85% would be not so great, right? And if you start to get 90 and 95%, the thing, it doesn't do much moisture removal at all, right? So the more you go toward a hotter outdoor temperature, we learned, the more every system on the planet is going to suffer from that, right? It's going to be harder to reject heat. We look at these, all of these percentages are higher when compared to their equivalents on the other side, right? 73, 71, 72, 69, 89, 86. So that's just physics, right? But there are systems out there where under these conditions, you'd be looking at 80% or 76%, or you'd have better moisture removal. It's one of the big wild cards that AHRI doesn't give a good way to compare systems, or way to compare systems, right? A lot of systems are, or a lot of, do I want to call them more expensive? I don't know. A lot of your systems out there will be bad at moisture removal, and a lot of systems out there are very good at moisture removal. And the thing is, sell the homeowner what they need, right? You don't always have to have a lot of moisture removal if your house is nice and tight, right? So if there's no such thing as a ton, which is how this thing started, what the heck is a ton then, right? Because it's clearly not 12,000 BTUs. What the heck is a ton? So how many BTUs are a ton is one of my favorite pop quiz kind of questions. How many BTUs are a ton? Right, 12,000 is the answer everybody gives, right? It's not 12,000, by the way. So it's 286,000 BTUs. It's actually 286,000 BTUs and change, but I don't know what the change is. It's off the top of my head. It's 286,000. Sometimes you'll hear 288, and that's when somebody reverse engineered the math because I forgot what the actual number really was. And it's pretty close, right? It's pretty close. 286, though, is technically the number here. There's 286,000 BTUs in a ton because air conditioning is something that someone invented. And they invented the concept of keeping a building cool before they had the refrigerant cycle, guys. They used to cool buildings with ice. And when Willis Carrier and Dave Lennox, two actual guys, sat down and started working out the standards they were going to use in their new refrigerant-based air conditioning systems, they decided that they were going to go through the gatekeepers, the engineers. You want to get yourself sold? Get the engineers to spec your product. Go to them. And engineers, they don't like to learn new ways of doing things, right? It's a pain in the butt, right? I know this way to do it. This is how all of my slide rules, because they used a lot of those back in the day, are based on this idea of how many, tons of ice a system would need per day. And so now we have this refrigerant cycle here, and it doesn't need to be replenished every day. We don't need a shipment of ice every day. So what they did is they took the 286,000 BTUs that you get when you melt 1 ton of ice, and they divided it by the 24 hours in a day. And they got 11,900 and change and said, why don't we just call it 12,000 BTUs per ton? And the thing about that story is, it's a true story. The thing about that is you melt ice in the middle of the room you're sitting in right now, or you melt it on the surface of the sun. When you change the state from solid water to liquid water, it absorbs the same number of BTUs, right? There are no variables involved. No, it absorbs the same number of BTUs, changing solid water to liquid water. That is a chemical process that has that's called the latent heat of water, and that's it, right? The refrigerant cycle is clearly a delicate process which will be affected by various things along the way, right? So all of these variables will affect the actual performance of that system differently than it would have back in the tonnage days, right? That's why I said there's no such thing as a ton. If you want my full sentence for that, is there's no such thing as a ton unless you're talking ice. So the good news is there's a couple bits of good news here. One, a lot of manufacturers, let's see if I got I have a fake one. Let's see if I've got one in here. No, I don't have my fake one. That's okay. So a lot of manufacturers will have calculators online. So if you want to go to the manufacturer's data and you don't want to use the chart, there are a lot of manufacturers that have them. In fact, here, I can show you, I know one off the top of my head, because Wrightsoft wrote it for this particular manufacturer. We've actually done this for a couple of manufacturers. Here's just one that I know the link to off the top of my head, right? And so what a lot of manufacturers will give you is they'll give you the ability to input the numbers, the outside dry bulb and the inside wet bulb and the inside dry bulb, so that the tool knows what those conditions are for the system you select. And then let's just filter out with the systems in some way, but it will show you the actual capacity of the system, sensible and latent, two separate numbers, so you know what the performance of that system is, right? And you could identify, what you're dealing with. So that takes us to the rules of the Manual S. And the rules of the Manual S are rule number one, and these rules are not actually ordinal in the book. I put the number one, number two on them. The rule number one is you have to have enough latent. If you don't have enough latent, you can't control moisture. Full stop, right? If your system does not have enough latent, it's the wrong system 100% of the time. Forget about it. That's the wrong system. Okay. Rule number two is don't have too much sensible, because I don't care how much latent you have. I had an energy expert once say, well, I had to put a 5-ton system in my house just to get the latent. That's not how that works, right? You put a bigger system in your house and you've exceeded the sensible load, the air conditioner stops running. We have a thermostat on the wall. When the thermostat is satisfied, the air conditioner doesn't run, right? The latent capacity that we were looking at on that Excel spreadsheet was when the system runs for an hour. If it doesn't run for an hour, it doesn't have that latent capacity. So you cannot exceed the size of the sensible by too much, and how much is too much we'll get to in a minute. Then there's not oversizing on the total. A lot of engineers will tell you that oversizing on total alone, in other words, you have enough latent, matter of fact, you have way too much latent, which, by the way, what is that? Too much moisture removal. You don't have too much sensible, but you do have too much total. So so the different camps who agree or disagree on whether or not that's, it is in the Manual S. That is the rule. Full stop. There you go. But in terms of the wisdom of it, there are engineers who will tell you that the longer you run the system, the drier it's going to get in the house, and eventually you're going to get to lower latent capacities, because you will have lowered the wet bulb temperature in the return. And the group of engineers who say that's not a problem will point out that the only way that happens is you've already removed the moisture, and so you don't have a comfort problem in regards to moisture, which is true. Moisture won't be a comfort problem, but short cycling creates other problems, right? Creates temperature swing issues. It creates more start and stop cycles, which is not good for the life of the unit. Like, there are distinctly downsides to being oversized on total. Although some engineers will tell you, and mostly the equipment engineers will tell you that it's not going to be the biggest problem compared to the other two. So how much is too much? Well, according to Manual S, a single stage, single speed system can be oversized by 15% or undersized by 10%. Okay, a two-stage system can be oversized by 20% and undersized by 10%. and a variable capacity system. That doesn't mean a variable speed fan. It means true variable capacity. It means more than 2 stages in the outdoor unit can be oversized by 30% and undersized by 10%. So I believe it's useful to know, because there's a little bit of an issue with that, guys. So taking off my Epic Trainer hat, there's a little bit of an issue with that when you look at smaller units. Because what we are dealing with there is the fact that you have a window of, so the homeowner's on a budget, or the builder, and it's going to be a single stage system. So I can oversize by up to 15%. I can undersize by 10. Not a lot of people want to do that, but if you will allow us to undersize by 10 and oversize by 15, that's a 25% window. If you don't want to undersize the unit, then it's a 15% window. I don't care if it's 15 or 25% though. The difference in percentage between a 1.5 ton and a 2 ton is 33%. Let that number sink in for a second. 33%. So there's a loophole in the back of the Manual S about using lower capacities for moisture removal. So that applies if you are going to oversize this by slightly more and it has lower stage capacities. There's some rules for doing that. They're somewhat complex, and I don't want to break them down right now in here. So this isn't about doing the math. And then there's Energy Star. And Energy Star takes those Manual S requirements and just puts them in their standard, right? 15%, 20%, 30%. There you go. Those are the recommended sizing standard for Energy Star. You know, they have an allowable range, though, that allows you to exceed that first number. It's double. Single stage, 30%. 2 stage, 40%. Variable capacity, 60. Now, the reason for that is multifold. My house, I have a 1 ton load on my house. I live in a small house. There's no oversizing by less than 15%. Right? So I complied by the Manual S rules when I did my submittals to the local power company. By Energy Star rules when I submitted to the local power company. Right? And I wasn't oversized. And the thing is when you're participating in Energy Star, if you go over that recommended line, you got to explain yourself. You got to give an explanation to go to the allowable range. But there is an allowable range, and it exceeds the hard line. And that's something to probably be aware of from the inspection side of things. The folks over at DOE have sort of identified there are exceptions to some of these rules, some common sense exceptions, which, I mean, frankly, that's why we pay inspectors, right? Is to be able to execute, the manufacturer recommendation loophole, or to be able to say, well, okay, well, if nothing else meets it, what's the standard here? There's a standard put out, the ACCA handbook put out, called the Manual 5. It's a quality installation standard. It says you should size the equipment by the Manual S or to the next half ton, right? If you can't meet the requirements in the Manual S, right? Because sometimes you can't. Sometimes you get a weird one, right? So let me really quickly show you what Manual S, the process of Manual S looks like when you're using Wrightsoft software. So if I take a load calculation that I've done, and I want to pick an air conditioner, right? So I wanted to pick a real air conditioner, by the way, for the loads that I did here. I told you it was a real unit. So you can see that I have one in here. And I'm not playing brand favorites. It's just one of the first ones that came up on my list, and is a pretty widely sold system. So you see here that, well, partly because I'm also streaming and doing this presentation, and I've got 3 other programs running in the background, and the program is taking its time here with the little swirly line, and it's going to do that, yeah, because it has the ability to go through all of the equipment data for anybody on this list that you see in red, right? And so we've got a bunch of red manufacturers in here. Those are all manufacturers that gave us their extended performance data, which allows us to check this little button right here. Select for Manual S. Have us go through that giant spreadsheet worth of data, right? We are going to look at this crazy thing. Where the heck is it? Oh, no, I've done it. I've put it behind. Hold on a second. Sorry, guys. Oh, boy. I've put it behind the stupid tool. There we go. behind the stupid toolbar for my presentation here. There we go. This amount of data for every matchup, right? Not every condenser, not every possible combination of these things. And it's going to bring up anything, a list of criteria. These all meet the load. And so going through that, crunching that data, it's about checking a box in Wrightsoft. And we actually have more than the ones that you see on the list here. There's a couple of brands for Wrightsoft that we have the ability to do this, but only if you have the branded version of the software, the OEM version of the software. So if you're a particular user of a particular brand, you can get that. And if I check that box and I select this and I hit OK, that system, what we did is we just crunched all of these numbers to find out what the real capacity of this system is and give us those actual BTUs in that capacity, and that's the unit that we're going to select. The last thing that I want to show you is that most load calculations actually have, when you look at the actual performance data, you look at what the actual capacity of the unit is, you look at the actual requirements of the manual S, most loads, most homes could be, there's no such thing as a 3-ton load. Most homes could be a large 3 or a small 2.5. You see, in that range, in that percentage range, when you play with airflows and play with coil matchups and play with this and play with that, you will find that if you allow yourself to pick anything under the sun, I might be able, let's see. And sometimes there aren't, so let's see how this goes. I definitely should have tested this before I made the bold statement. But there are often situations where in order to be able to satisfy, oh, no, it's not done. There are no 3 tons that meet this load. All right, well, if I go and grab a different one, that'll be true. And here, let's see. Well, that's not, here, I'll open up a load that I've done in Dallas. I'm sure I have a couple. All right, so here we go, Dallas. So there's a load. All right, my tech guys, ignore the flex duct. That's what the customers wanted. So if I go and, all right, yeah, that class was at a carrier facility, sure. So if I go in here, and so this is a 48, and yeah, so here's a 36, and yeah. So if I clear this out and I start looking for the units, I'm most likely going to be able to find a 3 and a 3.5, or a 2.5 and a 3, or yeah. So there's a 42 right there, right? I picked a 36. This one's a 42, right? A 3.5 or 3 all would actually meet this load and fall within that manual S criteria, right? So the rules of the manual S are, at their core, they're pretty darn simple, right? Know what the system is going to do before you pick it, and we can make that easy for you, right? Wrightsoft gives you the ability to just hit a little button and match that up, and then make sure you have the ability to remove moisture, enough moisture to keep the house comfortable. Go figure. Make sure you don't have too much temperature control, otherwise you're not going to do that moisture removal, and make sure you don't have too much total capacity. Okay. All right, that is my time. There's one question in the Q&A box. So, Jason, if you want to.
Yeah, I'll read that. Well, but I'm just one of my own, and
yeah,
that percent latent that you showed. So I down on the Texas Gulf Coast. I mean, is that not one of the most important things especially so the majority of HVAC contractors, how they're doing their whole house mechanical ventilation or fresh air requirements is running that duct to the soffit with a 6-inch duct with the controller, which basically, if it's 92% relative humidity outside, there's no smart, there's no inline humidity sensor in that. And
Yep.
so it's just bringing in that outdoor air. You're already on the Gulf Coast as it is. Is that not one of the most important things you would be looking at? Is that
It is, in my opinion, on the Gulf Coast, it is the most important thing, right? So if I go to, say, let's say Corpus, right? That's going to be fun, right? So we go to Corpus, and so what's going to happen is in your load calculation, right? If we're going to have outside air, so I should probably, if this is going to be a new construction home, we'll make it tight, right? That'll be like 3 air changes per hour, 50 pascals. But then we will add outside air according to the ASHRAE standard. And the load on that latent load on that, look at that. That is a 7,000 BTU latent load. If I do the math, and we're going to talk about it as a function of a percentage, right? So that's going to be 33,491 plus 7324. See, we never add that number up because you're not supposed to, right?
Yeah.
And so, wait a minute.
Yeah, you added 324, not 7324.
Oh, that will do it, right? So 33,491 plus 7324. There we go.
Well, and I've been advising the mechanical contractors down there for a long time now, is you've got to have some sort of smart whole house ventilation. In other words, if it doesn't have a humidity, if it's not sensing the humidity of that outdoor air when it's bringing it in and shutting it off when it's over X percentage, I mean, I just, for a couple $100 more, you can use smart whole house mechanical ventilation or smart fresh air. Or you're just using that dumb open damper that's just bringing it in no matter how humid it is outside. I mean, you can help yourself out a lot by using a smarter whole house ventilation strategy.
And there's a lot of building science that can go into this, right? I mean, like if I have a very large home, right, and I'm going to bring in all of the outside air for that big home into one of its 3 systems, that one system has a huge proportion of moisture removal that it all of a sudden has to do compared to temperature control. And so you're asking an awful lot of it, and that one area can become extremely uncomfortable. So maybe that, okay, we can do that. We can bring that cost down. So maybe your options are, well, we're going to have 3 small outside air intakes or 1 big one, but we're going to use an ERV. And we're going to reduce that moisture load so it doesn't overwhelm this one little system. Or we're going to use an inline dehumidifier in that. Or we're going to, but the biggest thing you can take away from this, the literal biggest thing you can take away from this, is there's 2 damn numbers at the end of the day.
Yeah.
For a reason. You're not supposed to add them up. They are 2 jobs. Latent temperature, moisture removal, sensible is temperature control. And you need to know when one of those jobs is a monster job and one of those jobs isn't, right? And understand how you would attack that problem. Yeah.
And you select the equipment appropriately because, basically, awesome. Okay,
because if you build a nice tight house with an ERV in Corpus Christi, you shouldn't need a ton of moisture removal, right? It's a nice tight house, right? And you have an ERV and you've dealt with that moisture removal, or a lot of that moisture, not all of it, of course, not all of it, but I mean, it's not going to be as bad as your biggest problem, child, will be the older, leakier house retrofit in Corpus, where it's uncontrolled how much that moisture comes in, and you, as the HVAC contractor, aren't in charge of it.
Right.
So.
Yeah. Wow. Yeah, that's it. Just the more I learn and the more I get into this, it's just so much more of a detailed science, and having to know what you have and what you're trying to get and what you're trying to do is just, it's so much more important than, oh, it's 2,500 square foot, you need a 5-ton. Just whatever the supply house carries, that brand, that's what you need.
Oh.
And, it's just scary. Oh, the one question, I was happy to have Wes Davis on the line.
Wes, I saw that. Thank you. Good looking out. I did not know that.
Yeah, he'll be giving a webinar for us over his ACA residential system design review forum that I'm trying to talk all code officials into requiring a permit so we can get more and more folks using the JS&D. But just for the other folks on here that can't read this, it says the 2015 ACA QI5 standard no longer allows the next largest size exemption. I guess that was allowed in the past is no longer allowed.
That is my bad. No, I need to get I need to like Wes offline if you can let me know if there's like an email list or something when you guys like shout out from the rooftops every time a new standard or the standard is updated. So I can just keep an eye on that. That'd be good because I hate it when I do stuff like that. I was teaching minimum velocities for manual D for like 5 years that I wasn't supposed to be. Because I didn't realize they changed the manual D standard. My book was old, so sorry about that.
I know we got one more question come in, and then also while I'm getting to this other question, if you could just speak briefly to that email conversation chain that I shared with you the other day, and we were talking about just in a general theoretical sense, when a HVAC contractor says, well, if there's a 25-degree temperature split and it's 105 degrees outside, my homeowners aren't going to be comfortable at 80 because they live in a canvas tent and that heat transfers immediate. So talk about that temperature split and how they need to.
And we talked about this a little bit in the first one of the series that we did a little bit. When you're choosing an outdoor temperature, one of the common misconceptions is that if we look at our Corpus Christi design temperature, it's 92 degrees. If we look at our, if I go to Dallas, right, there's going to be so many Dallases. I'm just going to pick one at random. It's 99 degrees, right? And the answer to the big thing people throw out at me is, hey, man, we get 53 hours that's over 100 degrees, right? 3 of them are significantly over 100, by the way, over 105. So what happens on that 105 degree day when I'm designing at 99, right? So one would assume that, except, by the way, this is not true. But one would assume, it's 95. If I design at 99 degrees and it gets to be 105 and I've designed it at 75 degrees inside, it's going to be 81, right? And sorry for the voice. If that's your opinion too, it's not right. That's not right. And I can see why people think that, right? Mm-hmm. But time is a very important function of what we're doing here. When a homeowner, so this is what I always like to say when I explain it to contractors. I know a lot of you guys aren't contractors, but when I explain it to contractors, if a contractor sells a vacation homeowner a system, an air conditioner, and does not sell them a Wi-Fi thermostat that allows that homeowner to turn on their air conditioner before they show up, they are going to have complaints because the average homeowner shows up to their vacation house, turns on the air conditioner when they get there Friday at 5 o'clock in the evening, right? And it's not going to be comfortable in their house like all damn night, right? It's going to be 2 a.m. before it's comfortable in their house. And why? Because every surface of that home is a thermal battery. Every piece of furniture, every wall, every door, it's all holding heat. There's thermal mass absorbing that heat. And you have to remove not just the heat from the air, but from all of the things inside the building. Well, it works the other way too. It takes time to heat up your house. And so the second it becomes, 99, goes to 100 degrees, it did not just tick the thermostat up 1 degree inside the house. That's not how it works. It takes time to heat up your house. And so if it hits 106 degrees outside and you designed it 99, I'm going to tell you it's probably going to get a little warmer in your house. Yep, it probably will, because it probably will have been over 100 degrees most of the day, and it has had that time. But is it going to be 81 degrees? No. And so the $1 million question becomes, well, then what do I tell my homeowner who calls on that day? And the thing is you don't wait for that day to happen to tell your homeowner something. That if you don't want to have, right, because this is, hey, we can, if we go to a variable capacity system, we can oversize it by more. I'm allowed to size it to a larger capacity if it's 2-stage or variable speed or variable capacity, right? So maybe I can sell you an air conditioner that will keep you comfortable all of the time if that's your expectation, Mr. or Mrs. Homeowner, without ever having to touch the thermostat. We have systems like that. They cost more. But if you want to be comfortable all the time, all I need you to do is what you would have done anyway, which is play thermostat games. See, what people are used to is they're used to oversized systems, which means that on the 95-degree day with an 80% or 90% humidity, they're having to turn the thermostat down because it's just not running long enough and they're humid, right? But homeowners don't know from humidity, right? Homeowners don't know it's humid. They just know they're uncomfortable. And so they hit the down arrow, and they don't think about it. They hit the down arrow. Hey, now it's comfortable in my house. Cool. And it's why so many homeowners think they're comfortable at 65 degrees. It's because they have oversized systems. But if I woke up in the morning and saw in the news that it was going to be 105 degrees all damn day today, if I turned the thermostat down in the morning before it hit 105, if I turned the thermostat down to 70 degrees instead of 75, and the air conditioner was able to make my house 75 degrees over the next couple hours, right? Or even better, I saw it on the news the night before, and I turned the thermostat down the night before, and I left it at 70 degrees. It will warm up in the house, but it will warm up in a way that maintains comfort. It won't exit the comfortable range, right? And it's much harder to do that on the other side of the fence if you have an oversized system, right? Because but the idea that you will always be comfortable all the time, no matter what, if you just set one thermostat setting, that is a high technology, expensive equipment idea. And by the way, how you sell that stuff. And the idea that you want to be comfortable all of the time, your best shot at comfortable the majority of the time is with the required, by the way, manual J conditions of 99 degrees. But on the hot day, because it's always the question, what do I tell the homeowner? Turn the thermostat down, right? You turn it down in the morning, seriously. And by the time they call, it is too late. But it'll work tomorrow. It'll work tomorrow. Just turn the thermostat down.
Yeah, it's amazing what a conversation with the home. Well, they entertain on the 4th of July party. Okay, well, if they're comfortable at 74 in the house on the morning of July 4th or the night before, turn it down to 70 or 69, and then they can help maintain, compensate for that increased load. It's not, this one oversized piece of equipment is not the panacea that too many people and consumers, and if I understand if you're an HVAC contractor and you're selling a system and the homeowner's insistent, it's taking the time to educate them how all of this stuff functions together and works, and how that they're going to have some skin in the game and work the thermostat a little bit. It's the science of it's fantastic. And I really appreciate you. We're about 15 minutes over, so I'm going to let everybody get back to work. Thanks so much, Alex. A really great webinar. I learned a lot. I just feel like I need more. There's just so much more I need to know. So let me know when part 3 is ready, because I'd love to have you back.
All right. Can I get, Wes, if you're still on the line, what's the name of the new book? The new one? QI5 standard. No, not the QI5.
Oh, the LLH.
Okay. So another thing that would tie into what we talked about here. So my house, my 1-ton house, that would fall under. So the manual LLH is a low load house. That's what LLH is. Low load house. It's becoming a thing where manual S is a little hard to apply in some of these applications, and LLH gives you some guidelines. It doesn't supersede it but it gives you some what to do in those situations. So just FYI.
I'm glad you plugged that, because we have had another gentleman I ran into at the ACA conference, John Sedin. He did an LLH webinar for us that we'll probably be running again in the next few weeks or so. So those of you folks that are on the webinar this morning, if you missed the LLH, we'll hope to be running a replay of that before too long. But I'll let everybody get back to work. Thank you so much, Alex. Really appreciate it. Thanks for joining us, everyone. Y'all have a fantastic day.
Awesome. Thank you.
Thanks.